I mean, if none of the vaccines work, then I mean, well, of course, if that happens, we'll eventually just have herd immunity because most people will get it. It'll be sort of unavoidable, and um, that'll be kind of that. But yeah, so all right. Well, we got a few things to talk about. Real big crowd today. Yeah. Hopefully, there's some more people online, but. Okay, so a couple things. First off, BSC number 3 will be up here hopefully in a few hours. So, and I'm sorry it's delayed again. Basically, the problem is that I have to rebuild the thing from complete scratch to start, right? I can't copy last week's, change the appropriate settings, and then send it live. Um, and which is really annoying. And if there's anybody that works for the Kansas company listening, then like you all deserve a boot to the head, um, because this is ridiculous that I can't just duplicate. Um, Qu'est-ce que ça? Qu'est-ce que ça? Oh, is this your?
He's being booked and left the jail.
No, Pablo Escobar got the.
That
Ah.
looks very nice.
Thank you.
So
Kind of sucks that his facial hair is covered in a mask.
well, that's true, but whatever. So, um, actually, the year that FISI won, I think the Halloween costumes was the year that they had everybody dress up as Star Wars something or other, including one guy who was R2D2, and that encompassed basically they started with like a 30-gallon trash can, and then like cut holes and stuff in it for him. That one was pretty good.
I think that might have been the current seniors.
Yeah. So no, that was definitely a nice one. So um, anyway, okay. So where were we? Yeah. So I'll get that thing up hopefully in the next couple of hours. And I'm sorry it's a little delayed. Um, the other thing that I need to upload and we need to talk about is basically since we're not going to do the final, then the points that would have been on the final need to get redistributed to everybody else. It'll be point socialism. Um, so no, it's too early for jokes.
Is that the ones that are in class right
Huh?
Yeah,
Yeah.
that's
Well.
a good idea. There you
Uh-huh.
go.
Well. Okay. Let's just see who's online.
See what's online.
Yeah.
View
Okay.
results, and then
So.
it's capital. Stuck in digital.
Yeah, let's see who's online. If you guys can sound off in the chat. All right, Mr. Sanchez. Oh, you can't hear what I'm saying. Okay, that would be. Coy, I think that's your problem because I'm definitely transmitting audio.
Here, I'll put it on my computer.
Yeah, double check that the audio is going through. I'm transmitting, so.
I binged it.
Oh, actually, you know what? I'm not.
I'll use
Okay, let's try this now. Much better. Okay, so the AirPods weren't connected. Coy. Hopefully that's better now. All right, looks like we got Coy, Farden, who's not even in the class, and Mr. Sanchez, and okay, Felix. Yeah, excellent. There's 4 people online. One of whom's not even in the class. He's in the calculus class, but I guess he has. Farden, you have nothing better to do today. So, all right. Anyway, so we need to redistribute points basically because the final category doesn't exist anymore because it's just going to basically be our part of our project. So I'm going to have you guys do. So there's really 2 projects that we're juggling simultaneously, and I need to formally assign the other one, which is to do something with this machine code stuff that we've been talking about. And I'll give you guys sort of a list of a couple of things to do with it. I won't make it as big of a project as I normally would. If we had like another week or 2 in the semester, then I think we would be able to do it Gucci. I think we did spin our wheels a little bit on figuring out Minecraft versus MakeCode versus whatever. It did seem, actually, as it turned out, that the majority of you guys picked MakeCode Arcade, which, like I said, if I had this all to do over again, I would have just had everybody do that. But I didn't want to take away Minecraft for those of you who had started playing with it. We've learned something, so that's all that matters. So the in terms of the project, the Minecraft or MakeCode or whichever you picked, um, basically what we're going to do is uh, sort of a combination of things. Sometime next week or early the week after, and I need to kind of think about the timing to make sure that this makes sense. What I want to do is spend a couple of days of class meeting individually with each of you to see what exactly it is that you're up to. Okay. And what are you doing? What progress have you made? Where are you going? What problems have you run into, et cetera, just to kind of get a quick read on where everybody is. Um, then obviously we've got more of this assembly stuff to talk. Um, then I want to one day do kind of a dry run of how we'll do the actual Twitch stream, just so that we're all on the same page from a tech standpoint. It'll be pretty easy. Basically, you all need to just install Discord, the desktop version, and on your machines, for those of you who have them, obviously, and then connect to my server, my teaching server. So basically, what we'll do is you will stream on the teaching server. It won't be live to the full internet. It'll just be on the teaching server. And then I will view what's on the teaching server, and that's what will pipe out to Twitch to go to everybody. And then I'll be able to easily switch between um, the different basically different inputs, which will be y'all's various outputs. Okay. Um, and there's basically 20 of you guys, so roughly speaking, will take about 4 or 5 minutes for each of you. And, kind of what I want you to do is sort of really quickly demo what it is you've made, and then briefly sort of talk about what's sort of one really cool part of it and what's sort of like one thing that like was hard that you figured out, kind of sort of thing, right? So it's sort of, yeah, I couldn't figure out how to do this, and then I did this, and bam, look how cool it is, kind of thing, right? So I mean, that's not very specific, but you guys get the idea, okay? Um, and then I'll have you guys also write basically a short paper kind of thing, sort of reflecting on the experience of doing the the stuff, sort of answering a couple of questions. Um, And yeah, the other thing I'd like to do with this is basically a little bit of peer review. So basically, like in the not next week, but the week after, uh, I've got a list written down somewhere of all of you guys that are doing MakeCode Arcade, everybody that's doing Minecraft, and everybody that's doing Scratch. And there's only, I think, 4 or 5 people that are doing regular Scratch as opposed to MakeCode. So there, what I'll do is I'll basically just have Canvas pair you up within those categories. So the guys that are doing Scratch will be looking at other people's Scratch because that makes sense, right? And then similarly for Minecraft and MakeCode. And just to give you guys a chance to get feedback from somebody else, right? And see, hey, this is cool, or here's this cool trick I found. Have you thought about blah? Hey, what's going on with blah? Just something basically to get a little bit of feedback from a real person uh, before you're sort of finished, if you will. Um, okay, uh, yeah, so that's pretty much the story there. So I need to write all this stuff down and publish it on Canvas so that we're all on the same page. But that's basically where we're going, because we've got what, 2 full weeks, followed by a Monday, right? And that's it. Okay, so yeah, I know, right? Well, and then the finals period. So, right, so the way this will work, right, is we have all of next week, all of the week after, and then Monday, Tuesday of the following week, we actually have classes. Wednesday of that following week is a reading day. So that's basically, there's no classes. That's time for you guys to prepare for exams, write papers and whatever. Then Thursday and Friday, there's finals. Then there's nothing on Saturday and Sunday. And then Monday and Tuesday the following week, which is the week of Thanksgiving, there's finals. And then you guys have to be out of here. I've heard that Dean Welch has dropped the hammer on move out by noon, right? GTFO. Yeah. So anyway, so that's sort of the cycle for the rest of it. So what I was kind of thinking is Monday of that partial week, we'll do our tech dry run. And then that basically gives us next week and the week after for talking more of this machine code stuff and also time for individual one-on-ones with me. Okay, so does that sound pretty good? I mean, we're not that far from the end, guys. So to put this in perspective, basically Monday, where we would be in a normal semester, is coming back from Thanksgiving, roughly, right? Because it'd be 2 weeks and then exams. So yeah. Anyway, all right. Well, so let's get back to the machine code stuff. What joyous fun that is. And oops. Let me. Okay. Let's just remind ourselves of the set of instructions that we had. So what can we do? We can move data to and fro. We can do addition of data. We can do logical operations with data, so and, or, and not. We can do bit rotation. We'll talk about that later. Sorry, I'm just getting a drink because I am parched. Oh, perfect. Well, and my wife's not here yet. So Dr. Gelman sent me a message yesterday saying that the brew would be closed this morning. Now, I came within an inch of just saying forget it and canceling class because there would be no coffee. But instead, I was kidding, right? I wasn't going to actually cancel class over the lack of coffee. So she's like, yeah, I'll just go to Starbucks. And I'm like, Ken has delivery? So she's bringing me Starbucks this morning. I know, she's awesome. So when she comes in with the coffee, you guys all have to start clapping. Okay. Yeah, anyway. Okay, so we can move data to and fro. We can do logical or arithmetic operations with our data. And then the one that will require the most intellectual power is to talk about the jump instruction and then the halt. Okay, so where maybe would be a good point to start is, so last time we loaded in some numbers. Well, and we looked at what the difference between opcode number 1 and opcode number 2 was. Namely, opcode number 1 loads from a particular memory cell, and opcode number 2 loads from, oh, hi, how's it going? Thank you. You were a lifesaver. So, yeah. Ladies and gentlemen, Dr. Gelman. So, yeah. So, anyway, so what was the difference? Opcode number 1 loads from a specific memory cell. Opcode number 2 loads a particular bit pattern. And in terms of the assembly, the only difference is the $ versus the hash mark. Okay, and I tried to make that similar to real assembly languages. It's not perfect, but yeah. So, and I've tried to be consistent here too, that dollar signs are always associated with memory addresses, and pound signs are always associated with specific numbers. It's a triple latte, so small triple latte. I like it kind of concentrated. When I was younger, I would get like a 16-ounce mocha, which was basically chocolate milk with a shot of espresso. And then eventually I started getting doubles. And then eventually I started getting smaller doubles. And now I'm on smaller triples. So my tastes have gotten much darker over the last 15 years of my life. So anyway, okay. So in particular, what we were talking about at the very end last time was, where's the subtraction operation? There isn't one, okay? We can build it by using several other instructions, okay? So to demonstrate this, first off, let me switch to, well, I guess I'll use Atom for this. Let me switch to a text editor or code editor that I like to use called Atom. We've seen this before. And then let me switch the OBS input so that everybody can see it. Okay, let's make sure that this actually shows up, because for some reason the full screen view doesn't really like to work on OBS, and I don't know why. Hey, it's working for once. Okay, so what I'm going to do is I'm going to put, oops, over here on the left, our note sheet, and over here on the right, some code. Okay, and then I'm going to blow this up so that you guys can see it better. Okay, and then we'll write a program. So, all right, so let's do subtraction. So let's do a subtraction problem that's easy. Okay, let's do something like 5 minus 2, right? Because we know the answer. So the first thing I have to do is I need to load the number 5 and the number 2 into some registers. Okay, so how do I do that? What are the commands to load specific numbers? Yeah, we're going to use opcode 2. So in assembly, it's going to be load which register. Let's say load registers 1 with 05 and register 2 with 02. Okay, now I want to be clear about something. Go ahead, actually. Go ahead. Okay. So we have written them in hex. 02 and 05 are hex numbers, even though they happen also to be the exact same thing in decimal, right? So if I wanted to write, say, the number 16, how would I actually type it? 10, right? Because it's in hex, right? So, or how about the number 10? If I wanted to do the number 10, what would I put? 0. What's 10 in hex? No, hex. 0A, right? Okay, so now in this case, because 5 and 2 are less than 10, the hex and the decimal representation are identical, so I don't have to worry about the distinction, right? Okay, so there's that. They are in hex. Now, I do want to be clear, though, what we have written there is assembly. This is different than machine code, okay? This is one layer up of machine code. Each instruction in assembly corresponds exactly to a 16-bit pattern of, okay, and what is that going to be? Let me tab over and put it here. What is it going to be for the first one? What's the opcode? 2. What's the register number? 1. What's the number that we're loading into it? 05. Okay, what about this one? 2202. The sequence of numbers? Okay. Yeah, so this instruction is something that we write for us as humans. But what does it really mean to the computer? It means this. So we have to translate each of the assembly instructions into a machine instruction, which is the sequence of numbers, right? Because if we go to our emulator, right, this dude, where am I going to put the word load? Nowhere, right? I have to put it in as the sequence of numbers, okay? But it's a lot easier for us as humans to write load 105. Okay, so we write that, and then once we're convinced we have everything correct, we turn it into that sequence of numbers. Okay, now let me be clear for how this works at the quote real computer. All right, so when I demoed this in Linux and I wrote some stuff and then I did a bunch of things in a console and then all kinds of stuff appeared and you guys were like, whoa, right? Okay, what was I doing there? I wrote something in assembly, or C, as the case may be, um, and then I used a program called an assembler to take it from assembly code and output the actual machine code. Okay, so I had a program do that part for me. There is no assembler for this language because I haven't written it yet. Okay, and I've been saying that for several semesters now, so you'd think I'd get off my butt and do it, right? So there is no assembler for the Brookshire architecture, or better put, there is an assembler, and you know who that person is? You, right? You have to manually assemble everything. Brookshire's one of the authors of the textbook. Okay, and so what we're looking at is the Brookshire machine because this particular architecture is described in his book. So he's not unique in the idea of coming up with an architecture that's sort of a toy architecture for teaching purposes. There are like 5 or 10 other ones. It's just this one happens to be in our book. Huh? Yeah. Well, no, because he did actually make it up. L'Hopital, right? So what Cole is referring to is how many of you guys have heard of L'Hopital's rule from calculus, right? Well, guess who came up with L'Hopital's rule? Not L'Hopital. So the basic story is it was one of the Bernoulli brothers. Uh, that L'Hopital, he was a marquis, so he was rich beyond his wildest dreams, and he basically paid one of the Bernoulli brothers like a retainer to like write him letters with his mathematical discoveries. So the Marquis de L'Hopital decided to write a calculus textbook. Okay, it's called Analyse de l'infini petit pour l'intelligence de courbeligne. Right, so the analysis of the infinitely small for the understanding of curved lines. Okay, so calculus in not so many words. Well, great. And so he put this thing called that now is known as L'Hopital's rule in his book. It didn't have a name before that, but his book was basically the first true calculus, what you would call a textbook, if you will. And a lot of people learned this method from his book, and therefore it came to be known as L'Hopital's rule. Okay, so anyway. All right, so yeah, so the Brookshire architecture is just the one described in the textbook. That's all, right? And that's the Joel's emulator here was designed with that architecture in mind. There is no assembler because I haven't written it yet. Now, one of these days, I'm going to get off my butt and I'm going to do something that takes this and automatically outputs that and then loads it all into his emulator. And you don't have to do that step manually. But for now, it's actually good that you do that step manually because what we'll see is how each instruction corresponds to a given machine instruction, okay? All right, so I've loaded the two numbers in, and now is where we have to put our thinking caps on, okay? How the heck do we do subtraction? Well, if we were to write this out by hand, right, what I would do is I'd say this. Okay, what is 5 as an 8-bit integer? 0, 0, 0, 0, 0, 1, 0, 1. And let me put a space in there just to make it a little bit more readable, even though it shouldn't actually be there. All right, what about 2? Okay, now, how do I do subtraction? I have to really do addition of the negative. Okay, so what I need to do is I need to figure out what is the negative of 2 as a signed integer, right? And so how am I going to do that? What do I need to do? I need to take 2, I need to flip everybody, so I'll call that F for flip. Oops. And then I need to add 1. Okay, so what does that give me? Well, okay, I got to start at the right, which is annoying here. All right, so I get a 0 carry. No, because this, right, all I'm doing is adding these two, right? The flipped version and 1. So I get a 0 carry, and then it's a 1 in all the other positions. Yeah? Okay, so this would be that. Okay, so this represents the number -2, right? It was the flip the bits and add 1. Okay, so how do we flip bits and add 1? Well, adding 1 should be pretty easy. We just load the number 1 in and then add it. The flipping the bits part is where we have to use our heads, okay? Well, okay. On paper, do we have to use our heads to flip the bits? No, you just freaking do it. It's on the computer. Where in my list of instructions is a thing that says flip all the bits? Well, okay, but yeah. Okay, it's easier than that. Okay, so let me take the number, let me take the original number 2 before we flipped it. Okay? All right, I'm going to, let me tab this over. I'm going to put the bit pattern of all ones. Okay, and then I'm going to do a bitwise XOR. Okay, so when I say bitwise XOR, what does that mean, bitwise? What do you think it means? Bit by bit basis. Okay, so I'm going to take, in this case, the far right pair of bits, 0 in the top number, 1 in the bottom number, and I'm going to compute the XOR of those two numbers. Okay, those two bits. And then I'll do the same thing for the second bit from each number, same for the third, fourth, fifth, and sixth, right? So I'm going to do this 8 times, but I'm doing it bit by bit. Okay, is that okay? All right, so what is 0 XOR 1? It's almost as if some of you guys, you know, have had circuit components on a basic skills exam. All right, what is 0 XOR 1? 1, okay? Right, so let's remind ourselves, what does XOR do? No, it doesn't. If they're both 0, what's 0 XOR 0? It's 0. What's 1 XOR 1? 0. What's 0 XOR 1 or 1 XOR 0? 1. Okay, so what is exclusive OR? It's one or the other, but not both. Okay, if both are false, it outputs false. If both are true, it outputs false. The only circumstance under which it's true is if precisely one input is true and the other input is false. Huh? Nor, yeah, okay. So, but nor is or plus a negation, not XOR, right? Okay, so what that does though is that, so it's not just that I'm using XOR here. It's that I'm using XOR along with this chosen bit pattern of all ones, okay? Because what's going to happen to the original number if it has a bit of a 0 and I XOR it against a 1? What am I going to get? A 1. What about if it started as a 1? I'm going to get a 0. So that does exactly what I want, namely flipping the bits. Okay, so it's not just, like I said, it's not just that I'm using XOR, it's that I'm using XOR along with this pre-chosen bit pattern of all ones. Okay, because I knew it would work. Okay, so the the XOR output is 1111, 1101, which is exactly the flipped version that we wrote before just by not being idiots. Okay, so how do I tell humans to do this? I just tell you to flip the bits. How do I tell the machine to do this? XOR against the pattern of all ones. Okay, does that make sense? Okay, now we got two problems. We need to, what is the bit pattern of all ones in hexadecimal? FF. Okay, so we need to load the number FF in. Okay, second, did you seriously make duck hunt, Evan? Oh, I'm sorry.
Yes, I did.
That's freaking awesome. In Python, no less, gentlemen. So um, this is, but of course, Owen is our, remember our 9-tower Hanoi guy, right? Yeah. So with the 360 no scope. Okay. Are you guys surprised when I like make jokes like that? Woke? That's not being woke. Yeah, that's being like being woke is that like I like campaign for women's rights or something, right? Like yeah, or like start a recycling program or something, right? Like okay, so I've got to load the bit pattern of all ones. I also need to load the number 1, right? Because I have to add that. All right, so let's load those two numbers in. Okay, so I need to load the bit pattern of all ones, which was FF, so that's the third line. And then the fourth line is to load in the actual number 1. Okay, Gucci? Okay, so now what? Now I need to take the number 2 and I need to XOR it against FF. Okay, so the number 2 is sitting in register 2. The number FF is sitting in register 3, and I need to XOR those guys and put the answer somewhere. Probably register 5 is a good choice, yes, for the destination. All right, so in machine code, in assembly, I would write XOR, register 5 is the destination. What two things am I XORing? The contents of registers 2 and 3. Okay, could I have written 5, 3, 2? Yes. Okay, same thing, right? Because it doesn't matter what order you do the XORing in. However, why do I have to put the 5 first? Huh? What do you mean? Yeah. So I have to put the 5 because that's where I want to put the answer. I need to tell it that. Okay, but the 5 is listed first. So in most of these instructions, the destination you specify first and the operand second. That is pretty consistent with most real assembly languages. Okay, so that's nice. Okay, now what is sitting in register 5 after that instruction is finished? The flipped version. What do I have to do to that? I need to add 1. Okay, so I need to add registers what and what? 4 and 5, and I need to put the answer someplace. How about register 6? Okay. All right, what is sitting now in register 6? -2. What was the whole point of this? Was to add that to 5. Okay, so I need to add registers what and what? 1 and 6. Okay, and put the answer where? How about 7? Okay, and then are we finished? We need to halt, okay? And now what we need to do is we need to translate these instructions into their corresponding machine code. We need to assemble it. Okay, so let me go back to the reference sheet. What is the opcode for XOR? It's opcode number 9, okay? So 9523, 5645, because addition is opcode 5, 5716, and then finally C0000. Okay, so any questions on how I got all of these things? Yeah, well, because every instruction has to be exactly 16 bits, and so if there's sort of unused bits, they've got to be something, so we just make them zeros.
Oh.
Okay.
But is the computer just go through and
Sort of, but it reads it 16 bits at a time, right? Okay, so what we have to do now is we have to take, let me go over to the Brookshire emulator. Okay, now here's something that's really handy. So you see up here in the URL, there's a pound sign and then a bunch of numbers. It's a little hard to read on the screen, I'm sure, right? But that bunch of numbers is exactly your code. So what I can do is I can delete that, and I can just start typing the sequence of numbers on the right. So 2105, 2202, 23FF, 2401, 9523, 5645, 5716, C000. Hit enter and then hit refresh. And now look what's in memory. Yes. Yeah. No. He just set up the website so that if you put the code in the URL, it will automatically load it into the appropriate spots. Okay. That's super handy because it means that in my notes, right, I have links to all of the examples with the code loaded in, and all you have to do is click it, and then bam, there it is. Okay. All right. So let me full screen this thing so we can see better. All right, so what I'm going to do is I'm just going to hit run here. So last time I stepped it, which meant that it would pause until I clicked again, right? If I run, it's going to automatically do all of that, and it's going to do it at half a second per step. Okay, so fetch half a second, decode half a second, execute half a second. Okay, so let's run it and just watch the registers. And what's sitting in register 7 when this is all over? 3. Look at what's in register 7 when everything was all said and done. Memory addresses, yeah. What do you mean the big box? What memory? It started in the answer? Oh, okay. So we'd have to use another instruction to take that answer and write it out to memory. So okay, the left are is the processor, right? And so the numbers are in memory inside the processor, but they are not out in memory, meaning RAM. Okay, nor for that matter are they in right. Okay, so let's back up a minute. On a real computer, what kinds of data storage devices do you have? Okay, you have your RAM. Yeah, but that's not usually ROM in the sense that it's, yeah, you've got a hard drive, right? So you have a permanent storage, you have RAM, which is big temporary storage, and then onboard the processor, there are registers. There are very few of them. They're super fast, but there are very few of them. And then on a modern processor, what else do you have? Yeah, there's cache, right? Okay, which is basically a very small amount of memory that's on board the processor. Okay, so that what we just talked about is called the memory hierarchy, right? So you have at the ultimate top registers. Below that is cache. That's all on board a processor. Below that is memory, which is physically separate from the processor, but is ephemeral in the sense that what happens if you turn off the computer? What's in memory? Gone. Okay? Then below that, you have permanent storage, which would be a hard drive, a floppy drive, an optical drive, an SSD, right? Any a magnetic tape. Believe it or not, you guys know cassette tapes. You could there back in the day, there were attachments for those things to computers, and you could use blank ones as data storage. Huh? Seems dangerous. Huh? Well, yeah. I mean, um, hey, we didn't always have like PCI Gen 4 SSDs, man. It used to be the Stone Ages for computing. Okay. Okay. So, point being, um, uh, there's a hierarchy of memory, right? So right now, all of our data in terms of the math that we just did is inside our processor, but it's not out in memory. Okay. If I want to store it out to memory, I have to store it out to memory. Okay, but I haven't written the instruction to do so. Right now, it just is sitting in the register and the program has terminated. Yeah.
So at some point, if we wanted to do more calculations with this same computer, we would have to start overwriting our registers.
Yes. Yes. Because you only got 16 of them, and really you only got 15 because I told you until next week, thou shalt not use register 0. Okay, it's special and has to be used specially. Okay, so let's run that again and see exactly the sequence of steps that's happening here. Okay, so I'm going to clear and run. Okay, so loaded in 5, loaded in 2, loaded in FF, loaded in 1. Did the XOR, added 1, added. Done. Okay, so all of that to do freaking subtraction. Okay, now on a modern processor, or really a processor from even the 60s, yeah, I know, right? They have hardware subtraction operators. Okay, which means that we could have done subtraction in a single operation, which would have been nice, right? I mean, because you notice we did addition in a single operation, right? You loaded in the two things you wanted to add, and then you added them. That was the end of it, right? So we had to go through all this rigmarole because there is no hardware subtraction operation on this particular architecture. Now, any other architecture under the sun that anybody actually uses does have a subtraction operation. Okay, so my bucket list, amongst other things, is to define what I would guess I call Brookshire 2.0, where I would take advantage of the fact that there are 4 unused operations. I would get rid of the float operation for addition and replace that with subtraction, okay, because nobody actually uses 8-bit floats, right? It's enough, like we can learn everything we need by doing this all with integers. Okay, so that. I would also make the website have a little checkbox where you could adjust the speed of the processor, because if you've got a really big program, the fact that it's operating at 2/3 hertz is kind of annoying. Okay, so I'd make like a turbo mode basically. The other thing, and this is where the big pile of work would be to write an assembler. Okay, namely where all you had to do was type in load 2 comma ff or whatever, and then you hit a button and it produces the actual machine code and loads it all in for you. Okay, there is no such program yet. You guys are that program. Okay. Now, that said, the programs that we're going to be writing for this are not going to be like complicated enough where, I mean, they'll be complicated enough that it would be nice to have that, but it's not like we've got thousands of lines of code here, right? So it's sort of good enough to get the idea by assembling by hand. Okay, so next time what we need to talk about is we need to start talking about how to do conditional expressions and then looping expressions. Okay, and we'll go from there. All right, well, have a good rest of your Friday, and stay tuned to a flurry of announcements and things on Canvas once I get everything fixed.